boys, here are some questions and answers in organic chemistry, stereochemistry. I think we have seen in the previous sessions about the carbohydrates, some 100 questions we have seen. So here are some more questions. This is a set of multiple choice and it will be very easier for you to answer. So let us begin with question number 1. Compounds which have different arrangement of atoms in the space. I think I told you about this and we just call it as the configuration. You must remember this. Configuration is the distribution, different arrangement in the space while having the same bond to each other sides are said to be called as position isomerism, functional isomerism, chain isomerism, and stereoisomerism. Here is the answer is D. You can read this out. Stereoisomers in his contrast, what a stereoisomer has contrasts with several structural isomers which share the same molecular formula but bond connections in there. This is wrong. I think this is something a mistake. Stereochemistry has contrast with structural isomers. By definition, the molecules that are students of each other represent the same structural isomers. So these all do not form the stereoisomerism. They come into different isomerism, function group, and all those things. But atoms in space, the configuration itself suggests that you have this. Okay. So this is the next question. Which of the following can make a difference in the optical isomers? Optical isomerism, I think you know what is the condition for this. For the condition for the optical isomerism is that it should have a chiral center or a symmetry. That these two are the conditions for that. And so you can see that which of the following can make a difference in optical isomers: heat, temperature, polarized light, pressure. So I think the answer is polarized light. What is the polarized light? Plain polarized light is the light which rotates. The light which is being reinforced into one plane of polarization. So C is the right answer there. So you can see an optically active substance is one which can rotate the plane of polarization of plane polarized light. So that is, you know, it has a rotation in different directions. It can be represented like this: a plane polarized light having its poles in all the directions. Okay. But when you pass it through the polarizer, the plane polarized light will be having only one direction. So it has to be passed through this polarizer. So this is a property that can be deflected by the optical isomers, that is the asymmetric chiral carbon atom only. Okay. So the next question is, which of the following Fisher projection is different from the other three? So you can make out all these are the carbon atoms there at the center. So it is asking Fisher projection is different from other three. One is singled out. Okay, what it can be? So you can see that there is pH group at all the places here, here, and here. So it is asking compound number 1, 2, 3, and 4. The answer is D. It's the fourth one. Why? When comparing, here also you have got pH there, so I just missed it out. When comparing Fisher projections, it is important to recognize the horizontal bonds. So what does he mean by the horizontal bonds? These are the horizontal bonds. Point out of the page, and vertical bonds point out into the page. That is, it comes up, this is coming up and this is also coming up. It comes like this. If a substituent is held in place and the other three substituents are rotated, the new structure is the same as the original structure. So the answer is D is the right answer. Why? Can you see that? All have got pH, H, OH, CH3, pH, H, OH, CH3, pH, H, OH, CH3, pH, H, OH, CH3. That is the rotations, I think, changes which you have to make. I told you in the class that changes we make have to be even number of times. Okay. So here this structure, if you change what is here, H comes to this place, OH should go here. Okay. Or if you take that, CH3 should come here and pH should go there. Here pH has come there and H has gone here. So that is one change. The next change is OH has come here and CH3 has come here. So as a result of this, you can see that CH3 is here, OH is here, pH is here, and H is here. All have made about 90-degree turnarounds. This should be the same with this case, but it is not there, so it is the singled out case there. Okay. So next question is 4. Which of the following terms best describes the following pairs of the molecules? So here is a pair of molecule. You must always remember that it comes like a CH3, CH2, CH2, CH, and CH. Here you got CH2, you got CH3. That is to say that there is a double bond present there, and there is also a double bond present there. If you have a double bond, now it naturally means that it is a geometrical isomerism. That is, okay, only geometrical isomerisms will have the double bonded compounds. Okay, that is the answer, double bonded compounds. So, or even you can call it as the unsaturated compounds. Unsaturated compounds. So the next question is what is the relationship between two groups in the following molecule? What is the relationship between two groups in the following molecule? It is for this I think you should know the cyclohexane. I think we have seen this cyclohexane, and I have told you to be very specific about the bonds that you put here. So sometimes you call this as axial and this as equatorial, and this as equatorial and this as axial. So this is axial and this is equatorial, axial, equatorial. So you can see if you have both of them axial, that means they are trans to one another. Okay, although it appears to look in the same side, but you must remember the important formula there that we say if you have A, it is called as a trans in a eclipsed format. It goes to that, and then E that is also comes to the trans. But if you have A and E and A, they come to the cis isomerism. Okay, so that is the right answer there. Axial and equatorial terms are described in the orientation of the single group with respect to chair conformation and therefore can be ruled out. The bromine and chlorine are both oriented downwards on the same side with the chair. So this is applicable to only the chair form. If you have a boat form, then the things will change in a different manner. For boat form, it is not the same. Okay, not the same. By definition, they are cis to one another, and in the cis form. But here, the D is the right answer for that. Okay. Next is the question number 6 we have. What is the stereochemical relationship between the following two molecules? This is also a cyclohexane. Okay. And this is also a cyclohexane. Right? So you can start numbering them. Suppose if you start from number 1 from here, this is 2, and this is 3, this is 4, this is 5, and this one is 6. You can number it likewise here. 1, 2, 3, 4, 5, 6. So all of them are in the same position. So you can see that one has got the same axial there, one is there. So you have got Cl there. And then CS2 CS3 is there for the third molecule, CS2 CS3 is there for the third molecule. So here it is difficult to find out whether it is axial or equatorial, but here you can make out axial and equatorial. Therefore these two aren't geometrical isomers, they aren't enantiomers. Enantiomers means they should have the mirror images, they should have the mirror images. There aren't even isomers, and these things are the identical. So the answer is D is the right answer there. So you can see that both molecules have the same molecular formula and the same connectivity. Each molecule also has 3 stereocenters marked above with asterisk, and we have done the numbering here. In the place of asterisk, we have done numbering is very easy. Okay, so therefore the D is the answer. The molecules are identical, and that is also done by this particular part. This is the shading. You can see the shading shade. Okay, that is the molecule is painted in our direction. Molecules are almost identical, but it is not the way to write. And which of the following? Next question. Which of the following is an alkane which can exhibit optical activity? I think for that you can directly go back to the answer, because writing a structure is sometimes more essential than just visualizing it. So neopentane is what actually you just write it as CS3, CS2, 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 and CS3. That we call as a normal pentane. That is the same thing as the neopentane here. So isopentane means you should have some it should be a similar to both the sides. And the next is the 3-methyl pentane. So it is written like this: 3-methyl pentane. So it is 1, 2, and 3. 3-methyl. This is the methyl group there. 3-methyl, 4, 5. 1, 2, 3, 4, 5. 3-methyl hexane is also there. So this one is 3-methyl hexane. Its answer is D. So 3-methyl pentane will not give you that particular activity. Here 3-methyl hexane, 3-methyl pentane shows optical activity, and 3-methyl hexane is this is written like this. Answer is D. Explanation: 3-methyl as shown below. So there is a confusion there. So let us just try to solve that out. So you can see that you got ethyl group here, you got methyl group here, and you got 2, 3 propyl group here, and you got hydrogen there. Therefore this is an asymmetric carbon atom. So 3 plus 1, 4, 5, 6, 7, 6. Okay, you can write this 3-methyl hexane. I'll write it again here. 3-methyl pentane you can write 1, 2, 3. 3 and CS3, CS2. So 3 means from the third there will be branching. 1, 2, 3. 3-methyl pentane means you should go for this CS2 and CS3. So you can see it is 4 and 5 there. So 3-methyl pentane, it doesn't show the optical activity. So this is wrong there. 3-methyl in the third position you got methyl group there, and you should have one hydrogen atom there. But what happens is here you will have one ethyl group here, and again another ethyl group there. Okay, so 2 ethyl groups, same groups will not give the answer. But rather instead of that, if you have one more, you use just to CS3 and CS3, you will get hexane. So it should actually be explained for hexane, and that should be that will get asymmetric carbon atom there if you have hexane there. So D is the right answer there, 3-methyl hexane. Then the next question is, what is the molecular formula for the alkane of the smallest molecular weight which possesses a C7H16? I think something is missing there. 8. I'll just try to find out. Some page is missing there. I'll try to put question number 8. Just a minute. Let's see. History gives me 4. Question number 8. So it says how many stereos or isomer are possible for what is the molecular formula? Okay, I'll take up this question later. So it's not clear. The next question is question number 9. Which of the following statement most accurately describe the stereochemistry between various cyclohexanes? So the cyclohexane you can keep in mind is that you should have uh, cyclohexane means what should come to your mind is like this, and like this. Three types. Cis 1,2 dihexane and trans 1,2 dihexane rotate plane polarized light in opposite directions and either in equal opposition or racing mixture. Okay. Cis and trans they cannot rotate, they are geometrical isomers. Okay, that is the wrong thing. Okay. The diaxial and diequital forms of trans 1,3 dihexane can be separated by differing in physical properties. So axial and equatorial are actually again mm, 1 and 3, 1, 2, and 1 and 2, and 1 and 2 and 4, 1 and 3 should be there. Okay, they actually possess physical properties. There is no difference in physical properties. For this diaxial diequatorial of trans cannot be separated by their physical properties. Okay. Only cis 1,4 diclohexane is achiral due to the plane of symmetry, and cis 1,4 diclohexane is the 1,4 diclohexane. Then the conformational isomers of trans 1,2 dichlorohexane and which are not intermediate but resolvable. So his explanation, the right answer is D. Conformational isomers of trans 1,2 dichlorocyclohexane. Trans 1,2 dichlorocyclohexane means, you can just put it like this. First one is this one, chloro, and second one is equatorial. Trans 1, 2, this is 1 and this is 2, dichlorohexane are enantiomers which are interpreted but resolvable. Means, if you just put a mirror image of this, you will get some other thing, some other isomer, mirror isomer, which is not interconvertible, but you can resolve it. Why? The resolve is, here chlorines cannot be positioned diaxial, but can only be axial or equatorial, vice versa. Diaxial, diequatorial, okay, they cannot get it, but it can be monoaxial. So it is to say that it is mono, and this is also a mono. So if you have di like this, it doesn't conform to any geometrical isomerism. So that is why trans is clearly given there. Okay. Then question number 10 is, which of the following is statement can be deduced about the stereochemistry of this compound? This compound is optically active because it has got stereogenic centers that creates cis trans isomers. This compound is optically active uh, because the compound contains a center plane or axis of. This compound is not optically active since there are no stereogenic centers. This compound is not optically active because of its symmetry. So what is the right answer there? I think probably it is A. This compound is optically active because it has got a stereogenic centers. What is that stereochemistry? You can see a biphenyl there. Here, this particular CC is a biphenyl type of compound. So this can give rise to optical isomerism. Optical isomerism. Therefore, that is what is being mentioned there. So this compound can give you rise to these geometry. So here it is. The question is, what is the molecular formula for the alkane of the smallest molecule which possesses a stereogenic center? Okay. So these are the C4H10, C5H12, C6H14, and C7H16. And the last one is appearing here, C7H16. Okay, this is the right answer there. So you must keep in mind about the CnH2n plus 2. It is telling that C is a compound which show optical isomers have a chiral carbon. So an unsymmetrical alkane show the optical isomerism. Unsymmetrical alkane means which is not symmetrical. Okay, that is chiral. 6 carbon atom and 8 carbon atom alkane is not the answer. You can see why. What are the options given there? C6H14. If you see C6H14, C6H14, it is an alkane, CnH2n plus 2 formula. If you just put it there, C6 means 2 into 6, 12, 2 plus 14, so it is not symmetrical, it is symmetrical. And likewise, C8, C6H16 is also symmetrical. C5H12 is also symmetrical. C7H16, C7 to 14 plus 2 16. You have to draw individual structure. You have to draw individual structure to find out. Okay, individual structure to find out this. Okay. So here is the end of the 10 questions there. We will just see the next session. Thank you.